Hello, my name is Achintya Haldar. I am from University of Arizona. I'll be talking to you on reliability estimation of structures excited by dynamic loadings using stochastic finite element method. Now, I have been working in this area for over 5 decades. I'm going to share with you some of my work. The motivation of developing stochastic finite element methods are the following. Basically, I'll give you very basic concept first. It is basically integration of first order reliability method and FEM. Then I will introduce the concept of form method too. I will show some example with a case study, and at the end I'll talk about performance-based seismic design, PBSD. Now, because of the difficulty of the subject, it is mainly possible for me to talk the mathematics in detail. I will give you references at the end of my presentation. Safety evaluation using realistic behavior of structures and loadings, similar to procedures used by the deterministic community, are necessary. Finite element method is very desirable because deterministic community use it very regularly. But what we have to do, we have to include uncertainty in the finite element formulation. And the uncertainty related to resistance related, load related, connection and support conditions, linear and nonlinear behavior, and for different performance level must be incorporated appropriately. Now, when we talk about dynamic loading, we could use random vibration approach, but it is not going to satisfy the deterministic community. That is the reason we have to develop stochastic finite element method. When I was a student long time ago, we used allowable stress design concept. What we did, we reduced the load so that the structure behaved linearly, and the uncertainty in the load with the safety factor would basically give the safety for the overall design. Then for concrete, we started using ultimate strength design. When the design concept matured to consider uncertainty-related issues, then we developed LROD, load and resistance related factor design concept. It is in early 80s, and more recently, at least in the US, we are trying to incorporate, we call it performance-based seismic design guideline. I'll talk very briefly later in the presentation. Now, to consider realistic performance, we must consider uncertainty in the environmental loading, like earthquake loading, structural variable, like structural geometry, material properties, and boundary condition, a major factor. I'll talk briefly later. Then boundary condition, basically, generally we assume fixed pinned and roller. In reality, there is no fixed support. Moment of inertia of the support must be infinity. Most of the connections are either fully restrained or partially restrained. And if we make proper assumption, appropriate assumption, our design would be very, very different. Now, our reliability is always estimated with respect to a performance function or limit state function. When limit state can be expressed in terms of all the design variables and the performance requirement, we call it explicit limit state function. And for that, we can use now, we call it first order or second order reliability method, or we can also use Monte Carlo simulation method. But when the limit state function is implicit, it is very, very difficult problem. And for that, we could use Monte Carlo simulation method or stochastic finite element method, as I'll be talking here today. Now, for stochastic method, finite element method, why you develop? There are other methods you can use. You can use first order, second order, Taylor series method, Newman expansion, Carr-Newman, Leib orthogonal expansion, polynomial chaos. These methods generally do not need the information on distribution, and acceptable results are generally obtained for small random fluctuation. And in that case, really, a form-based approach would be appropriate. When you use any finite element algorithm, efficiency of the algorithm is very important. Most of the time, people use, we call it displacement-based finite element method. All the computer programs commercially available or in use, they are based on displacement-based finite element method. We use called trace-based finite element method. It is a little bit complicated, but it has many desirable features, particularly when you need to consider uncertainty in the variable. As I said to you before, I wrote a book on the topic, and it is published by Wiley. I'll talk a little bit more about it a little bit later. Now, in the context of first-order reliability method, we call it form method 1. It is basically when the performance function is available in explicit form. What we do, we calculate the direction cosine at the checking point. When it converges, we put it on the equation because it is available and calculate the reliability index beta. So it is very straightforward. So basic concept is there. Initially, we start at the mean values of random variable. Since this is not the actual failure point, it is going to be away from the actual failure point. This is the actual failure point, and after second or third or other iteration, we try to calculate the shortest distance from the origin to the limit state function in the reduced variable space. Now, for our problem, we are, as I said, our limit state function is implicit. We do not have that equation we are talking about. So what we did, we then try to combine assumed stress-based finite element method with first-order reliability method, and that gave me the stochastic finite element method. The challenges are, we have to first define the uncertainties inputted, and then how we propagate from, for a very large system, from element level to the system level. Then we have to calculate some response characteristic, and then we have to validate this model using limited data, available data. Now, when we are talking about large scale computational model, there are techniques I am suggesting here: reduced order model, surrogate model, Bayesian method, stochastic dimension reduction method, or efficient Monte Carlo simulation method, but they are not going to be applicable for our class of problem of interest, and that is why we need stochastic finite element method. Now, before we go forward, we have to talk about form method 2. It is basically we develop for implicit performance function. We cannot take the derivative of the limit state function, but we can do the derivatives in a numerical way using Newton-Raphson type recursion equation like this. And in this case, instead of beta, we calculate beta from the shortest distance from the origin to the reduced to the performance function in the reduced variable space. So basically, form method 2, as in form method 1, x is the random variable, u is the displacement in the limit state function, s is the load effect, and u we can express as q, and d is the global displacement, and q is the transformation matrix. And to get that gradient vector form to implement form method 2, these are the equation. We need to follow this particular equation. There is Jacobians I am using. It is derivative of a variable with respect to another variable. I cannot go too much into detail because it is complicated. So basically, it tells us basic concept is evaluation of 3 partial derivatives and 4 Jacobians. And these derivatives and Jacobians would depend on whether the problem is linear or nonlinear, 2-dimensional, 3-dimensional, and performance function used and other things. So limit state function, basically the iterative stage, same thing we do for form method 1, we are going to use same iterative state. We are going to define the limit state function. We don't have really, in this case, it is algorithmic form. So we'll assume the initial center point to be the mean values, and then we are trying to calculate the shortest distance using form method 2, and we'll get the result we are looking for. The desirable feature of stochastic finite element is reliability evaluation made should be robust and not problem specific. We can solve any type of problem using this particular concept, so long it can be represented by finite element. And since deterministic community is very familiar with classical finite element method, they are very willing to accept this particular concept. Now, performance is always evaluated with respect to limit state function. We call it serviceability limit state. It could be, we define it this way: delta is the actual displacement, and delta limit is the allowable deflection, and we can calculate the corresponding reliability index using form method 2. For strength limit state, since we are going to use finite element method, every element or most of the element have both axial load and bending moment. So we use interaction equation of the form given in the AISC manual. Here, applied bending moment, axial load, bending moment, capacity, and other things are given. And these are the 2, at least in the US, we use based on the amount of axial load applied to the element. So we use that to calculate reliability for our structures. So what we are going to do first, we are going to demonstrate the application of this concept for a 2-story steel frame building. Then after that verification, we used a case study to show the application potential. Then we'll talk about the connection rigidities. What is the implication if you use the connection rigidity more realistically? And then we are going to talk about a little bit performance-based seismic design. So this is a 2-story building, very small. We apply excited it by earthquake time history, and all the variables we consider are random variable, as you can see. And then we use serviceability limit state. And there we used, in case 1, we use 9 random variable. And you can see Monte Carlo simulation may take 23 hours. But here we can get that result within very limited time period. Now, we also tried case 2 with 7 random variable. We disregarded 2 less important variable. Monte Carlo simulation required 23 hours, but again, we got the very similar result, but with much more efficient way. When we talk about strength unit state, the same thing. Here you'll find beta value, and by Monte Carlo simulation and these stochastic finite element methods, they are very similar, but it is much more efficient. Again, it takes about 23 hours of excitation, running of a continuous running of a program. After we are satisfied with the verification, then we took a case study, a 13-story steel building damaged severely during 1994 Northridge earthquakes. Please look at this girder in this column. It suffered significant amount of damage. And we took the time history recorded close to this particular building, and we tried to calculate the reliability index for interstory drift and the column. And you can see for allowable here reliability index is negative for all three cases. And you know, reliability index beta, when it is 0, probability of failure is 50%. When it is negative, it is more than 50%. And you can see serviceability is probability of failure is 100+%. And for strength, it is 90% or 86%. That means it is going to fail. So we are extremely satisfied that this particular algorithm predicted the behavior of the frame very, very accurately. It could be that building was designed long time ago. They did not check the serviceability limit strength, and they also did not probably use linear evaluation technique, not nonlinear regression technique, and that may have caused some of those weaknesses in the design. Now, next time to talk very briefly about the flexibility of the connection. Generally, I said fixed support is not available, and flexibility of the connection is expressed in terms called moment relative rotation curve. So here I am using an equation one of my colleagues developed, Ralph Richard. You can describe it in 4 parameters: elastic stiffness, plastic stiffness, moment, and the shape parameter. Now, what we did, we took a 2-story building and excited by a time history. And instead of using FR connection, we assumed to be fully restrained connection. We assume it to be curve 1, curve 2, and curve 3. Curve 1 is very close to FR connection, and curve 3 is very thin connection, and the third one, curve 2, is in between. And here we calculate those 4 parameters of the Richard curve. We estimated uncertainty in the variable, and we calculate the reliability index for FR connection and PR connection for curve 1, curve 2, and curve 3. You can see curve 1 close to FR connection, but they are not the beta value for serviceability and strength limit state. They are not same. You can see FR is giving very, they are saying it is safe, but it may not be safe even if we use some PR connection. And you can see when it is curve 3, it is the weakest one. Reliability index could be negative for both curve 2 and curve 3, indicating that it is not going to survive. Then very briefly, we want to talk about performance-based seismic design. In the past, we designed for life safety. But now we realize most earthquake caused significant of damage, and it caused tremendous loss of economic activities of the region. So this design concept gives the engineer or the owner the alternatives to satisfy different performance requirement under some reliability requirement. It is a very sophisticated reliability-based method, but the code committees or PBSD committee did not suggest what method to use. Actually, there is no method available to calculate the corresponding reliability. The basic concept is that after earthquake, if you want the user to go back, it is called immediate occupancy. Then old practice life safety, and it is called collapse prevention. We want to prevent. This is a new concept. We are going to talk about it a little bit later. And these 3 levels are in terms of return period. You can see the life safety 10% in 50 years, or return period is 475 years, and collapse prevention is almost 2,500 years. And you can see you can control that by defining allowable drift. Allowable drift for immediate occupancy would be very small compared to collapse prevention. It is your common sense you can use to figure out this thing. And there, what we did for collapse prevention, for life safety, and immediate occupancy, we use the reliability index for relatively good soil, beta soil. And in America, to consider uncertainty in the earthquake loading, we need to consider multiple time histories, and we use 11 time histories. And you can see the reliability index, how it changes. You can see for 50% immediate occupancy, reliability index could be very high, but it could be very small, relatively small for collapse prevention. I then take a soil type D, and soil type D, if you do not have the soil site information available, in America, we use soil type D, and you can see we again calculate the corresponding reliability index, and you can see the reliability went down significantly for soil type D. So to conclude my discussion, really, we developed a very major reliability evaluation technique. It would take all sources of nonlinearity and uncertainty. We identified that serviceability limit state could be more critical than commonly used strength limit state. It would provide an alternative to stochastic finite element method, and it is also alternative to classical random vibration approach. As I said, this is the book I wrote before. This is the newest book I published about 2 months ago. If you want to know more about this, you need to refer to this particular book, and you will get the idea you are looking for. Thank you for listening to me. This is the campus I am here, and thank you, and hopefully you will figure it out on your own. Many thanks.